We're going to finish up Chapter 7, covering Sections 8 and 9. We're going to look at the work done by a variable force and power. Alright, so let's start with 7.8. Work done by general variable force. Alright, so what happens when the force isn't constant while you're trying to find how much work is done? Okay, so let's first talk about one-dimensional. You can divide the area under the curve of the function of force into a number of narrow strips of width x. Alright, so if this is our force, and it's going to be changing, it's going to be increasing, right, as the distance increases, then we can divide this area under it into a bunch of chunks, right, with these rectangles here. Now we can choose x small enough to permit us to take the force, fx, as being reasonably constant over that interval. Right, so if we make these pretty small, the force is reasonably constant inside this interval. And we'll call this interval delta x. Alright, well, if we let f sub j average be the average value of f of x within each of these intervals, or the jth interval, right, that's just saying that any, the number of interval, where j is just the number. So the work done by the force in the jth interval is just going to approximately be whatever the force is, right, at that point, multiplied by whatever this delta x is. Alright, so it's basically the area under the curve. Now, if I wanted to know what the total work is, I would just take the summation of all of the works of each of these rectangles, which is just going to be the sum of all of the force values multiplied by the delta x for each of them. Alright, Wj is then equal to the area of the jth rectangular shaded strip. Right, so that's just saying that Wj is going to be the work done by this individual strip. Alright, we add this all together, we get the total work. Alright, so this is basically what an integral is. If we go on to the next page, we can make the approximation better by reducing the strip width, delta x, and using more strips. Alright, so if you make this delta x smaller and smaller and smaller, we can make the approximation better. Alright, so what we really want to do is, in the limit, the strip width approaches 0. I want to take the limit as the strip width approaches 0, making it smaller and smaller and smaller. And then the number of strips then become infinitely large, where we have a lot of strips, and then we could actually get an exact result, alright, of the actual area under the curve. Alright, so doing that, we just take the limit as x approaches 0 of our sum to find what the total work is, and that's just going to be the integral from some value of x to some final value of x of your force function, right? So this could be a function, it could change, or it could be something like 2x squared or something like that. And then dx, right, which is our just little increment of x, right, just some little increment here. Okay. So if we wanted to look at the work done by a three-dimensional force, all you'd have to do is look at it in unit vector notation. All right, so let's first start by looking at the forces in unit vector notation. Basically saying that we have the x component of force in the I direction, we have the y component of force in the j direction, and the z component of force in the k direction. Sorry, this is just the normal unit vector notation we've been using. Alright, so what our little dr segments are going to be is then just this dx in the I, dy in the j, and dz in the k. Alright, where dx is going to be the x component of the displacement vector, dr, and so on. Okay, so our work then is just going to be the dot product of f dot dr, right? Because remember our work equation is f dot d, or f dot x. Alright, so this is just going to simply be our x component times the increment dx, our y component of force times increment dy, and then our z component times our increment dz. Alright, so what does this look like to get the total amount of work? All we would have to do is take the integral, right, of both sides, and what we end up getting is the force in the x direction times dx from x to xf, xi to xf, so it's the initial x position to the final x position, and then so on and so forth. You have your y component all right, with your y limits, and your z component with your z limits. Okay, so looking at the work kinetic energy theorem with this variable force, a particle of mass m is moving along an axis, an x-axis, and acted upon by a net force Fx that is directed along that axis. Now the work done on the particle by this force as the particle moves from position xi to xf is going to be given as this, and we've seen this before. Now, in the last slide rather. Now if we look at, we break this force into ma, right, because force is equal to mass times acceleration. Then we can go ahead and take the integral, or we can look at this, and this is actually going to be just dv dt. All right, so again, we know that the acceleration is dv dt, and this can be written as dv dt, or excuse me, dv dx divided by dx dt. All right, and we can do that because these are just going to cancel out, right? But if we rearrange it slightly, if we take this dv dx separately, and then we multiply it by our velocity, which is dx dt, we can do that. So we just sort of rearranged the variables a little bit and got a different result. All right, therefore, our work is going to be actually mass times the velocity times dv. All right, pull out the mass, you get the integral of the from velocity initial to velocity final times velocity dv, right? And then that ends up being our change in kinetic energy, which is our work energy theorem, right? Work is equal to our change in kinetic energy. All right, so let's go ahead and do an example. First example, let's look at 2D integration. All right, so we're given a force. All right, it has an x component that is variable and a y component that's not variable, so the y component is constant. With x is going to be in meters, x on a particle changing only the kinetic energy of the particle. How much work is done on the particle as it moves from these coordinates? So these are our x coordinates here. All right, this is going to be our initial x, this is our final x, and this is going to be our initial y and our final y. Does the speed of the particle increase, decrease, or remain the same? All right, so let's go ahead and look at this. Well, we know that our work is just going to be the sum of each of the components, right? So it's going to be the integral, and then in the x direction we're going from 2 to 3. So here's our initial and here's our final. So from 2 to 3 times the force, which is going to be 3x squared, right? Times dx. So that's going to be our x component. Now we want to add our y component, and that's going from 3 to 0, right? Because we're starting at 3, we're going to 0 in the y direction, right? Multiplied by our force, and then dy, right? Our force is not variable in the y direction. All right, so simplifying this so that we can solve it, we're going to pull out the 3. This again is from 2 to 3, x squared dx, plus, pull out the 4 because that's constant, from 3 to 0 dy. So we just have the integral of dy at the end. All right, so what does this look like? Well, this is going to be 3, and then the integral of x squared is going to be x cubed divided by 3. You always increase the power by 1 and then divide by that number. All right, so it's going to be x cubed divided by 3. All right, so that's going to be 1/3 times x cubed. And this is going to be from 2 to 3 plus 4 times y. The integral of dy is just going to be y, because right now technically we have y to the 0, right? Because there's y to the 0 is 1, so there's no y there. To take the integral of that, it would be y to the 1 divided by 1, which is just y to the 1. Okay. Okay. All right, so that's going to be 4 times y, and that's going to be from 3 to 0. Now, solving these out, these 3's are going to cancel out, so we don't have to worry about that. So we have x cubed, and we put top minus bottom when we solve these out. So it's going to be 3 cubed minus 2 cubed plus 4 times 0 minus 3, right? Because 0 minus 3. All right, so this just gets us a result of 7.0 joules. All right, so that is the total amount of work done on the object. Now, the positive result means that that energy is transferred to the particle from the force, right? So it's a positive work, which means you're giving it energy. Thus, the kinetic energy of the particle is going to be increasing. Because k is equal to 1/2 mv squared, its speed must also then be increasing. If the work had come out negative, then the kinetic energy and the speed would have decreased. All right. So now let's look at power. All right, the time rate at which work is done by a force is said to be the power due to that force. If a force does an amount of work, W, in an amount of time, the average power to the force during that time interval is just going to be given by this equation. So the average power is going to be our work divided by our time. All right, so basically it's the amount of work you have done in a certain amount of time. Now, the instantaneous power is going to be the instantaneous time rate of work, of doing work, which can be written simply as our derivative of work divided by our increment of time. So it's some increment of work being done in some small increment of time. That's going to give us our instantaneous power. So the SI unit for power is going to be joules per second, right, because you have work divided by time, and we're going to call that a watt, which we've seen before. Usually you see power measured in watts. Like electrical power, and that's the same kind of thing here. So we're going to measure power in watts. The unit is going to be a capital W. We need to make sure we don't confuse this capital W with the W of work or with the W of weight. We have to make sure we're keeping them straight. Now, in the British system, the unit of power is the foot-pound per second, and often we use horsepower, especially when we're talking about vehicles. All right, so again, if you have 1 watt, all right, it's going to be 1 joules per second. Converted to foot-pound, you have your conversion factor there, 0.738. 1 horsepower is going to be 550 foot-pounds, or roughly 746 watts. All right. So let's look at something about power. So we know that our equation, power is equal to our little bit of work over a little bit of time, or increment of work over an increment of time. Well, if we write out our equation for this increment of work, that's just going to be the force times the cosine of theta dx. All right, because work is going to be force times distance times cosine of theta. This is divided by an increment of time. All right. Well, if I just rearrange this slightly, I can say it's going to be force cosine theta multiplied by dx dt. All right, I just separated the dx dt. Well, we know the dx dt is velocity. This is velocity. So power is just going to simply be our force times the velocity times cosine of theta. And what does this look like? Well, this looks like a dot product. Right? This is just another way of writing the dot product. So really, our power is going to be the dot product of our force vector with our velocity vector. Right? And this is, again, going to be instantaneous power. All right, so here's another equation that you can use for power. Okay, so let's go ahead and finish up with an example. All right, the figure shows that a constant force F1 and F2 acting on a box as the box slides to the right over a frictionless floor. So the box is sliding in this direction. You have a force applied to the left, and you have a force applied up and to the right. Force 1 is horizontal with magnitude of 2 newtons. Force 2 is angled upward at 60 degrees to the floor with a magnitude of 4 newtons. The speed V of the box at a certain instant in time is going to be 3 meters a second. What is the power due to each force acting on the box at that instant, and what is the net power? Is the net power changing at that instant? Okay, so let's look at these questions individually. First, we want to see what each of the powers is due to the force. All right, so to do that, we're going to use the equation that we just found with power. So power is going to be equal to F1 times the velocity times the cosine of theta 1. Oops. Right. Plugging values in for that, we have 2.0 newtons for the force, times our velocity is 3 meters a second, and then times the cosine of 180 degrees. Oops. All right, it's 180 degrees because our velocity is to the right and our force 1 is to the left. So we have 180 degrees in between them. Also, we need to note here that this cosine 180 is really taking care of the signs of any of the, positive or negative sign. The 180 is sort of dealing with that. It's the angle between the two vectors. So we do not need to include a positive or negative sign in either our force or our velocity. Okay. So this just gets us our power 1 is going to be negative 6.0 watts. All right, our power 2, right, due to the second force, is just going to be F2 times the velocity times the cosine of theta 2. So our force is going to be 4.0 newtons times the velocity, which is 3.0 meters a second, times our cosine of theta, which is going to be cosine of 60 degrees in this case, because we have velocities to the right, force 2 is up and to the right, and an angle of 60 degrees between them. All right, so we just find that our P2 is going to be 6.0 watts. All right, so those are each of our powers due to each of the forces. So now we want to look at what the total power is. So our net power is simply going to be P1 plus P2 is equal to negative 6.0 watts plus 6.0 watts is equal to 0 watts, which means that the net rate of the transfer of energy to or from the box at this instant is going to be 0. Thus, the kinetic energy of the box is not changing, and so the speed of the box will remain at 3.0 meters a second. Therefore, both P1 and P2 are constant, the powers are constant, and thus, so is the net power. Okay, that's it for this lecture and for this chapter. We'll see you next time.